Good morning and welcome back to Heat Transfer. Today we are going to finish up a few of the problems, or writing up a few more equations for some of the nodes that were on the previous problem from chapter 5, and then move into our coverage of more in-depth coverage of convection. So I'm going to start sharing my screen so we can get back to that problem from the last time and write a few more of those equations. Let's see here. Well, let's see, looks like it lost it. Let's see, hold a second. There we go. Okay. So from the last time, we were considering this L-shaped bar, and I wanted to present this particular object because we wanted to consider how the geometry would affect the writing of the equations, the node equations, based on the use of the energy balance method. And also the last time I explained that if you wanted to solve this problem by an exact analytical method where you are applying the general heat equation to solve for a continuous expression of the temperature variation here, which would be a function of x and y, you would have to actually split this problem into 3 subdomains so that this top portion would represent a rectangular section, and here there would be another domain to represent a rectangular section and a third domain to represent a rectangular section, because if we're solving this problem, this was the reduced expression of the general heat equation, we'd have to have just 2 boundary conditions in the x and 2 boundary conditions in the y for that particular problem or for a particular domain. And so we'd have to split this entire domain into 3 subdomains and then write expressions of an equality of the fluxes across the boundaries where we make these artificial or imaginary cuts in the total domain so that there will be a balancing of the heat fluxes across those boundaries. But again, if we can use a numerical method to solve for the temperature distribution, it just means we cut the domain or discretize the domain by establishing nodes throughout the network, or to establish a network, and then we write equations for that network of nodes. Now here in green, I label all of the nodes for which the temperature is unknown. So on the left side of this bar, where the temperature was TA, I didn't need to label those. You could label them, and it just would be that let's say if this was node 0 here, node 0 would just have a temperature that would say T0 is equal to TA. So rather than give these nodes numbers, we just use the boundary condition that the established temperature was TA. And we started writing equations for some of these nodes. Now for each of these nodes, we have to take into account the area that is shared with the surrounding nodes. So for node number 1, there was an area on the left that was a delta y over 2 tall by unit 1 into the page there, so that the expressions for the heat transfer between node 1 and the node to the left, node 1 and node to the right, node 1 and the node below are going to be based on these surface areas that are defined according to the way that we discretize the domain. Here, this bottom surface for node number 1 is a delta x wide by unit 1 into the page. This area on top, where there's convection heat transfer with surrounding fluid, is a delta x by unit 1 into the page. And so when we wrote those expressions for the area for the heat transfer rate from above and the area for the heat transfer rate by conduction below with node number 3, those were those defined areas. And then for the generation that we were considering that's occurring in this block, the generation is the amount of generation that's actually occurring inside that volume or that area that we see here, which is a delta x or a delta x wide and a delta y over 2 tall times a unit 1 into the page. So that represents a volume occupied by this material so that we can take into account the effective generation on the temperature of that node. So the last time I was writing expressions for some of the key nodes just to indicate how you would write expressions for the equations or write the equations that are representative of those node equations. Why some are being divided by 2. Okay, Renee, the drawing that I'm making here of these dashed orange lines are indications of the length and height of the volume that is occupied by that particular node. The node spacing is delta x in the x direction and delta y in the y direction. So when we discretize the domain, each of these nodes is a delta x in distance left and right, and a delta y in distance up and down. The volume or the area that is represented by each one of these nodes is indicated by the dashed orange lines. For all of these interior nodes, node number 5, node number 3, node 10, node 11, node 12, and node 13, all of those represent an area that is a delta x wide by a delta y tall. All of the nodes that fall on a boundary, none of those will have an area that's a delta x by delta y. They are some fraction because they fall on the boundary. Node number 1 is only 1/2 of delta x by delta y because it's only a delta x tall and a delta x wide and a delta y over 2 tall. Node number 2 is representing an area that is only 1/4 of a delta x by delta y because this length is a delta x over 2 and this length is a delta y over 2 to represent the area for which node number 2 is the average temperature. So for node number 2, when we look at the heat transfer between node 2 and node 1, it's occurring across a boundary that's only a delta y divided by 2 tall. When I look at the convection, for the convection that's occurring on the top surface, this length is only a delta, I'll start with just going the order that I wrote them. From the right-hand side, this boundary on node number 2 is only a delta y over 2 tall for heat transfer that's occurring with the surrounding fluid. So H times T infinity minus T2 times delta y over 2 times a 1. This length is only a delta y over 2. For the heat transfer occurring from above by convection, this length is only a delta x divided by 2. And the heat transfer occurring with node number 4, from 4 into 2, that length is only a delta x divided by 2. So these are indications of the areas perpendicular to heat transfer here by conduction between node 4 and 2, by conduction between node 1 and 2, by convection with the surrounding fluid, and then the generation that's occurring is in the volume, which is this surface area that is projected a unit 1 into the page. This is a delta y over 2 tall by delta x over 2 wide times a unit 1 into the page. So this expression of the generation, I'm writing out the actual lengths. I mean, this is 1/4 of delta x by delta y. If I just multiply these two terms together and then multiply it by unit 1. So the areas or for each of these nodes is directly defined according to the grid spacing that is delta x in the x direction and delta y in the y direction. and we use the resultant geometry to define volumes for the generation and lengths for the heat transfer that's occurring by conduction or convection on a boundary, where that area is the area for heat transfer between the surrounding node and the node of interest, or the surroundings if it's on a boundary. So rewrote equations for nodes 1, 2, 6, this inside corner node, and that was the last one. So here I would want to go on to some other nodes that, you're welcome, some other nodes that have some other considerations. Well, they're all the same considerations. The sum of heat in plus the energy generated is equal to 0 for all of these nodes. So when I'm looking here, let's say at node number 9, it's another corner node that has convection on the top, an applied heat flux on the right, conduction from node 8 on the left, conduction from node 14 below. So here, if I'm writing the equation for that node, using the same convention, I'm going to write heat transfer from the left, from the right, from the top, from the bottom, and then the generation. So from the left, this is heat transfer by conduction from node 8 into node 9. So this expression becomes K times T8 minus T9 divided by the distance between the two nodes, which is a delta X, times the surface area where the heat transfer would occur, which is a delta Y divided by 2 times the unit 1 into the page, plus the heat transfer from the right. Well, this is just by an applied heat flux. So this is Q dot sub S times the surface area. That surface area is a delta Y over 2 times the unit 1 into the page. The heat transfer from above is due to this convection condition. So this is the heat transfer coefficient times T infinity minus T9 times the surface area. That surface area is a delta X divided by 2 times the unit 1 into the page, plus the heat transfer by conduction from node 14. So this is K T14 minus T9 divided by the distance between the two nodes, which is a delta Y, times the area perpendicular heat transfer, which is a delta X divided by 2 times the unit 1 into the page, plus the generation that's occurring. That volume would be defined as a delta X divided by 2 times a delta Y divided by 2, which just gives me that surface area. Then I multiply by unit 1 into the page to make that a volume, is equal to 0. And so then that becomes the node equation for node number 9. And we would proceed through writing all of these equations. Let me get let's say the 19 here, which is on an insulated boundary. We didn't do any insulated boundaries at the last time. So for node 19, where we have insulation, again, insulation just indicates that there will be a heat flux equal to 0 on that surface where insulation is applied. So for node 19, it's a corner node, so it's only a delta X divided by 2 wide and a delta Y divided by 2 tall. And we'll, oops, here, there we go. So that there's no heat transfer from the bottom because there is an insulated condition. There's heat transfer from node 18 across this boundary that's a delta Y over 2 tall. There's heat transfer from node 14 across this boundary that is a delta X divided by 2. And there's a heat flux on the right-hand side through an area that is a delta Y divided by 2. And of course, we have also the generation. So here, this becomes K times T18 minus T19 divided by delta X times a delta Y over 2 times the unit 1 into the page, plus the heat transfer from the right, which is coming from the applied heat flux. This is Q dot sub S times a delta y over 2 times a unit 1 into the page, plus the heat transfer from above, which is from node 14. So this is K T14 minus T19 divided by delta y times a delta x over 2 times the unit 1 into the page. And I'll just put in here plus a 0 for the heat transfer from below, because there's an insulated condition. Heat transfer can't move into node 19 or out of node 19 through that bottom surface due to the insulation. And we have the generation occurring in a volume that is a delta x over 2 wide, a delta y over 2 tall, times the unit 1 into the page is equal to 0. So we can move through all of these nodes and write equations exactly in the same way, and we would end up with a system of equations that's 19 equations, 19 unknowns, and they would be solved simultaneously. And of course, here we want you, if you were solving this by hand, we want to use the matrix mathematics here. Let's see, yeah, such that you would end up with a coefficients matrix that would have 19 entries, which would just be the coefficients on the nodes T1 all the way down to T19. So this column vector would just be T1, T2, T3, all the way down to T19, with the coefficients in each row representative of the coefficients multiplied by those nodes for each equation. So for for the equation for node 1, all the way down to the equation for node 2 would have all these coefficients, and then the constant, which would just be based on those things that were constant in the equation, and move them over to the right-hand side so that we could take the inverse of that coefficients matrix multiplied by the constants, and that would give us the temperatures for each one of those individual nodes. Now that's what's actually happening in the background if you're using something like an equation solver. So if you use something like MathCAD or any other package that has equation solvers, once you've written all of these equations, you don't have to go through the trouble of identifying the coefficients. It would do that for you, and in the background, it would solve the equations by that method. But those coefficients and constants, let's say for node 1, the coefficients would be identified as those constants multiplied by any of the unknowns, which would be T1, T2, T3, all the way through T9 in node equation 1. So here I would have to group all of the coefficients multiplied by T1. So for T1, here I have this would be a minus K delta X times delta Y over 2 that's multiplied by the T1 in the first term, a minus K delta X, or minus K times delta Y divided by delta X times 2. That would be a coefficient, and an H times delta X multiplied by the T1 here, and a K times delta X divided by delta Y. All of those could be combined and represent a single coefficient multiplied by T1, where the thermal conductivity, the spacing, the heat transfer coefficient, all those things will be specified in the problem statement to actually solve for the temperature. And here for T2, we have, that would be multiplied by K times delta Y divided by delta X over 2, or divided by delta X times 2. That would be a coefficient multiplied by T2. And for T3, K times delta X divided by delta Y. So those would be the coefficients multiplied by T1, T2, T3. But then for T4 through T19, since they don't appear in this equation, the coefficients multiplied by those variables would be zeros. And the constant, there would be a constant. So we move this term to the right-hand side of the equation. So that would just be the negative of this term. And we'd also have another constant that would be H times T infinity times delta X. That will be a constant that we move to the other side of the equation. So it becomes a part of that value that is a constant. And also this expression of K times TA times delta Y divided by delta X times 2. because TA is a constant, the temperature on the left side of that wall, that's a constant. So those three terms would have to be moved to the right-hand side of the equation if we were writing a matrix or using a matrix representation for these simultaneous equations that would result as this network of equations that is the node equations from node 1 all the way through node number 19. So here, this expression for the temperature distribution is, though it has a lot of equations, the expressions of those equations is simplified, or is a simple expression of the sum of all the heat in plus the energy generated is equal to 0. So though we have a lot of equations, they are linear. It's a set of linear equations that we can solve by simultaneous equations or by matrix inversion because they are related through the temperatures here. And so the use of computers to solve these kinds of problems is very advantageous because they're not, there are no terms that are squares, square roots, etc. Here we're just solving systems of algebraic equations, which are very quickly and easily solved as long as the quantities are appropriately defined. If you miss a minus sign or misevaluate, let's say, a surface area or a volume, you can get some error in your calculated temperatures. But often once you calculated T1 through T19 and you add them or you visually represent them through colors or intensities of colors, you can see, or even if you're just looking at the magnitudes on a plot, on this plot, if we replace all of these numbers with the actual values of the temperatures that we would calculate from the node equations, then you can see, based on the generation and the boundary conditions that occur in this problem, you could at least qualitatively consider, do these temperatures make sense here? If I have generation occurring, we have a constant surface temperature here, convection on these upper surfaces, a heat flux, and an insulated condition. Well, I would expect that the highest temperatures here are going to be along this boundary where I have an insulated condition and where I'm putting the heat in. Because if this temperature is a constant and convection is occurring, with all the generation that's occurring in the material, the heat is going to leave through the boundary that is at TA, through the boundary where we have the heat transfer by convection. And if heat transfers from a high to a low temperature, if I'm putting heat in on this right-hand boundary here, this far right-hand boundary, then all the heat that comes in is going to move out of these surfaces on the left, the top, on the left and on the top, or the upper surfaces here. No heat can move through this boundary. So the highest temperature in this system is going to be actually the temperature at node 19, because none of the heat can move to the right because we're applying this heat flux. None of the heat can move downward. It can only move from node 19 towards this top surface and towards the left surface. And heat transfers from a high to a low temperature, or from higher temperatures to lower temperatures. So the heat would have to move to the left and upward. So this node that is at the bottom right, qualitatively, I don't know what the temperature is, but I know that this should be the highest temperature in the system. And there are the temperatures at nodes 14 and, well, particularly at node 14 is going to be quite high. At node 9, because we're receiving a flux and there's heat transfer out of the system, node 9 would have a lower temperature than 14, and 14 would have a lower temperature than 19, but the relative temperatures are going to be dependent on the actual values. What is the thermal conductivity? What is the generation? What is this heat flux? What are the magnitudes of the heat transfer coefficient and the ambient air temperature, and of course the temperature at TA? But we can always determine, after we've calculated all the temperatures, do those temperatures physically make sense based on the conditions that are specified in the problem, with knowledge that heat transfer is always going to be from a high to a low temperature. That's what drives the heat transfer. And actually, let me go ahead and I'm going to write an equation for just one of these interior nodes. And again, those are 3, 5, 10, 11, 12, and 13. Those are nodes that don't lie on a boundary. All of those will have exactly the same form because they're all a delta Y tall. They're all a delta X Y. They all have generation occurring, and that heat transfer by conduction is occurring with the surrounding nodes. So again, 3, 5, 10, 11, 12, and 13, all interior nodes and would have the same form. So if y'all look here at let's say node number 10, and just consider that our heat transfer from the left, from the right, top, and bottom are all just from the surrounding nodes. At the left is the temperature, that's TA, which is the temperature of this entire area that's around that node. For node 10, it's this entire area, that's delta X by delta Y. Node 5, node 11, and node 15 here. All of those have heat transfer that would occur across these boundaries that are on the left, right, top, and bottom for these nodes. So from the left, we get K times TA minus T10 divided by delta X, and the area here is delta Y by unit 1 into the page. From the right, node 11, this is K T11 minus T10 delta X by delta Y times the unit 1 into the page. From above, from node 5, so this is plus K T5 minus T10. Here, the distance between the nodes is a delta Y, and the area perpendicular to heat transfer is a delta X by unit 1. And from below, which is from node 15, T15 minus T10 over delta Y times a delta X by unit 1 into the page, plus the generation that's occurring. That area is a delta X by delta Y projected by unit 1 into the page is equal to 0. And this would be the same form written for all the interior nodes, in that the area on the left, the right, the top, and the bottom are all going to be defined by a full delta X and a full delta Y for those expressions of area for heat transfer between that node and the nodes around them. So this method of writing these equations allows us to write a system of equations that we can then solve for the temperature distributions. Now, again, those temperatures that we calculate are for each of these nodes that here I've indicated in green, and they will be considered to temperature, the average temperature for this entire node, or in this entire area where that node is the node for that node is representative of that average temperature. So, there is temperature variation that occurred, let's say for node number 10, all of this area is said to have a temperature that is at T10, but we know that there are multiple temperatures that would exist. There'll be temperature variations as functions of X and Y throughout this entire volume, and node T10 is the average temperature of all those. Now, if I needed greater resolution, I would just decrease the value of delta X and delta Y. That would yield more nodes, but that would also mean that for all of those additional nodes, the area for which that node is representative of the temperature gets smaller, because delta X and delta Y gets smaller, such that the smaller I make the area for which that node is representative of a temperature, the closer I'll get to what would look like a continuous temperature variation in X and Y, as I would have more nodes inside this entire domain, and I would get a better resolution. That would also yield a better picture if you were going to visualize the temperature variation throughout the object. If I have more temperatures, then I can have a better representation of temperature variations throughout the entire object. So that's how we would end up with temperature distributions. And typically, if you're looking at something like the results of a numerical analysis, let's say for heat transfer, if you were using a software package, or you're doing a thermal analysis and you get a nice picture of temperature variations throughout the object, that is just based on discretizing the domain so that you have lots of temperatures in the X direction and in the Y direction, and you assign colors to the temperatures, and according to the variation in that temperature between, if you establish, I don't know, let's say at 0 degrees is blue, at 100 degrees is red, and you can use other colors in between or just grade between those two temperatures according to the gradient between blue and red according to 0 and 100 degrees. You can assign different colors, and it allows you to visualize the temperature distributions throughout the object, and just give you a qualitative representation of temperature variations in the object so that you can perform analyses. Now, if I wanted to calculate, once I have the temperatures here on the top surface for node 1, 2, 4, 6, 7, 8, and 9, these temperatures will all actually be higher than T infinity. So that if you were asked, well, what is the heat flux out of this top surface by convection? Well, I know that the temperature across this boundary is a temperature that is TA, because this node is representative of this temperature for this entire 1/4 of a block. That would be a delta X by delta Y. Here, this entire length would have the temperature that is the temperature that was calculated for node 1. This would be the entire temperature. This length would have the temperature that is T2. This one would have the temperature that's T2. This entire length that would have T4. Here in this corner, T6, T7, T8, and T9. So if you were asked, well, what is the heat transfer rate out, or let's say through this surface, this upper surface here, then I know that heat transfer by convection is occurring along this entire surface, and I've segmented the surface so that I've calculated these average temperatures that occur across each of these lengths. Well, the heat transfer rate by convection, let's say once the temperatures are calculated, that heat transfer rate through the top surface would just be equal to the sum of the heat transfer rate for each of those nodes. And that heat transfer rate would be by convection. So once I've actually determined the temperatures, here this would include the temperature that is TA for this section on the top surface, T1, T2, T4, T6, T7, T8, and T9. So the heat transfer rate from just this section that has a temperature that is TA, Q dot, and I'll write this. This is going to be by convection here. From that top surface, if I start with the one that's at a temperature that is TA, this becomes the heat transfer coefficient times TA minus T infinity times the surface area for the convection. Well, this is a delta X over 2 wide times a unit 1 into the page. So this heat transfer rate that's occurring just on this area here that has a temperature that's TA would be the first contribution. And I would consider the contributions made by each one of these nodes that has a unique surface area associated with it. So for node number 1, this area is a delta X wide by unit 1 into the page. So the contribution from node number 1 would be the same heat transfer coefficient times T1 minus T infinity times delta X by unit 1 into the page. For node number 2, which is at this corner, well, I have an area that is a delta X divided by 2 and a delta Y that is divided by 2, where heat transfer is still shared with this common fluid, and the temperature over this entire block here is whatever that temperature calculated to be the temperature of node 2. So I can write this expression as H times T2 minus T infinity, and I'll just sum those areas. This will be delta X over 2 plus delta Y over 2. Both of those multiplied by unit 1 into the page to give me an area. So this is the area on the top of node 2 and on the right of node 2 that's exposed to the convection. So here again, the top and the right of node 2 that are both exposed to the convection that's occurring. And we would just continue around this entire surface that includes nodes 4, 6, 7, 8, 9. So that all we're doing is considering heat transfer. There's a heat transfer coefficient times the temperature difference times the surface area. And so we would just keep writing those expressions until we have all of them. And that allows us to write the heat transfer rate by convection out of the top surface of that object. If you were asked, well, what is the heat flux into the object on the right-hand side? Well, that would just be this heat flux that will be specified times this entire surface area here. If we were asked for any, let's say if we wanted to know, well, what is the temperature gradient in the object that is, let's say, at the top here? The temperature gradient, let's say, in the Y direction. Well, the temperature gradient in the Y direction for this top surface, well, on this surface here, the temperature at this node and on the entire left side is just all at TA. The temperature gradient, let's say, at this surface in the object would be T3 minus T1 divided by the distance in between the two. So, or actually, because we're moving in the positive Y, let me draw my coordinate system here. This would be positive Y and positive X here. So a temperature gradient is second position minus the first position. So this would be T1 minus T3 divided by delta Y would be the temperature gradient at this surface in the object. And that is just an indication. So here, T3 would be greater than T1 for heat to move out of the object and into this fluid. So this would be a negative value in that there will be a low temperature minus the high temperature divided by the distance between the two. And that would tell me what the temperature gradient in the object is at this upper surface. Now here, T2 and T4 would be different values. But if I wanted to consider, well, what is the temperature gradient in the vertical direction at node number 2? This would be T2 minus T4 divided by the distance between the two. And we could also calculate, well, what is the temperature gradient in the X direction? This would be T2 minus T1 divided by delta X. And that tells me what the temperature gradient in the X direction is. And we can do that anytime that we have nodes in the X and Y direction. We can determine what the temperature gradient is at any position just based on the temperatures that we would have calculated already. So once you have the temperature distribution the actual calculated values after you've written the node equations to solve them. You can answer questions about temperature gradients. We know that heat fluxes are just minus K times the temperature gradient. So if the temperature gradient is just the temperature difference over a distance, we can calculate temperature gradients. We can calculate heat fluxes, and we can use the areas to then calculate heat transfer rates. So once we have temperatures for a given object, we can answer all the heat transfer related questions associated with that particular object. Now here I was talking about the convection. And convection is defined by Fourier's law as a heat transfer coefficient times a delta T that actually drives the heat transfer times the area over which that heat transfer is occurring. So to consider in a little bit more depth, what we're actually looking at when we talk about depth and convection is a definition of that heat transfer coefficient. Newton's law of cooling just says that the heat flux by convection is just the heat transfer coefficient times the temperature difference between a surface and the ambient temperature, and the ambient fluid temperature. The heat transfer rate by convection is just that heat flux by convection times the surface area over which it's occurring. So this becomes H times Ts minus T infinity times that surface area. Now, anytime that we're talking about convection, we're considering a moving fluid, so that if this is a solid surface with a surface temperature associated with it, here we usually indicate some fluid velocity, V, and an ambient temperature, T infinity. And actually, I think in this text they use U infinity, where U infinity is just the free stream velocity of the fluid, and T infinity is the free stream temperature of the fluid. So that if this fluid is moving over the surface, and if Ts is greater than T infinity, then the heat transfer rate would be from the surface into the fluid. Now, when this fluid is moving, let's say if the wind is blowing or a fan is blowing, or if this is liquid where we're using a pump to move fluid over a surface, this is what we would call forced convection. And forced convection just means that we have some means by which we're using the inertia, or we're creating inertia in the fluid for it to move over a given surface, such that when there's a temperature difference between the fluid and the surface, we will have heat transfer. If the two fluids, or if the fluid and the surface are both at the same temperature, there will be no heat transfer because there will be no temperature difference between the surface and the fluid. Now, we'll still have all of the hydrodynamic considerations, like pressure drops due to the no-slip condition. The hydrodynamic part of the problem still would exist, but if there's no temperature difference, there's no heat transfer. When there is a temperature difference, not only do we have to consider the thermal part of the problem, but we also have to consider the hydrodynamic part of the problem. That's one of the complexities associated with convection, is that we're not just looking at the heat transfer portion on its own, because we do have to consider how the fluid is moving and its effect on the heat transfer that would be occurring by convection. Now, in addition to forced convection, we have what is called natural convection. So if I take the same surface here with a given surface temperature, and we have a fluid temperature, T infinity, but we could consider here that the fluid is not being forced. Ts is still greater than T infinity, And what happens here is that the air or the fluid right next to the surface would still receive heat by conduction because of that no-slip condition. We have molecules in contact with the surface. If those molecules in contact with the surface become a higher temperature, Ts, than the rest of the fluid at T infinity, we have buoyancy forces that are taken into account. For all fluids, whether they be liquids or gases, as the temperature increases, the specific volume increases or the density decreases, such that that molecule of fluid would want to move up and away from the surface, so that we would have the movement of particles upward and away from the surface. And of course, due to conservation of mass, if those particles move up and away from the surface, then other particles move in to replace them that have a lower temperature, and that will also give rise to convection. And again, we just call that natural convection, in that as the molecules of the fluid increase in temperature, their specific volume increases, and so they move up, or their buoyancy forces, by the more dense molecules around them, pushing them up and away from the surface in the opposite direction of gravity. So here, the difference between the forced and the natural convection is that the heat transfer coefficients associated with natural convection are just much lower, because here we're depending on the differences in the specific volumes of the adjoining molecules, rather than using a fan or some other means to actually move the fluid over that surface. But when we're talking about convection, those are the types of convection when we're considering no phase change that are often considered. But there are lots of other considerations that we have to make when we are making convection calculations, because all the work really is going into determination of this heat transfer coefficient. We can easily measure surface temperature and ambient temperature, and of course the surface area, but that quantity that defines the heat transfer rate or defines the heat flux is in this value of the heat transfer coefficient. And again, it's called a coefficient and not a property, because the expressions will change, or the heat transfer coefficient can change based on the type of fluid it is, what the geometry is, and the kind of flow that actually exists. So when we are considering convection, it is strongly dependent on fluid properties, where those fluid properties that are most have the greatest effect on the heat transfer are going to be the viscosity, the thermal conductivity, the density, and specific heat. Now, the viscosity primarily has to do with the hydrodynamic considerations. The more viscous the fluid, typically the more viscous that fluid is, the higher the rate at which the velocity boundary layer is going to grow. The thermal conductivity is a measure of how well does that fluid conduct heat. Now, here we're talking about convection, but we never want to forget about that no-slip condition. There are always going to be molecules right next to the surface that have the same temperature and the same velocity as the surface. So if the surface is not moving, a no-slip condition says that the velocity of those fluid particles right next to the surface also have a zero velocity, and other molecules have to slide past them. So even when we're talking about going back to hydrodynamics, when you have a turbulent flow, right next to the surface, you also have what's usually be referred to as a laminar sublayer. And at the bottom of that laminar sublayer, where we would have molecules of fluid right next to the surface, heat transfer has to occur by conduction through that stationary set of molecules that are actually attached. That heat flux through those molecules is defined by conduction, not by the heat transfer coefficient. So the thermal conductivity becomes a quantity that has to be considered. And then, of course, the combination of the density and specific heat is an indication of the amount of energy that is held inside or stored by the fluid, or any the fluid, or whether it be in a liquid phase or in a gaseous or vapor phase. So those are the important fluid properties, and we'll use those to help to define the heat transfer coefficient. Also, this heat transfer coefficient is going to be dependent on the fluid velocity. For any of these conditions, or either of these conditions, whether it's forced convection or natural convection, the faster those molecules are moving, the higher the heat transfer coefficient will be, and thus the higher that heat transfer rate will be. And that's just because as the fluid is moving, if it's moving at a higher velocity, there's a higher rate at which, in this case, for this forced convection, there's a higher rate at which cooler molecules will come in contact with this surface to facilitate and to enhance the heat transfer as we increase the velocity of the fluid. So that will give us higher heat transfer coefficients. And then we also have to consider the surface geometry. And actually we'll say surface, I'll try to write it this way, the surface, and that will include the geometry, and the roughness. And that the roughness would allow us to make considerations of typically transitions between laminar and turbulent flow. And then the geometry can be a combination of, is it a consideration, is it a flat plate like what I've drawn here, and we'll indicate as a flat plate? Is it a spherical shape? Is it a cylindrical shape? Then with geometry, there's also the consideration of the orientation. For this problem, where I've drawn that the fluid flow is parallel to the surface, if I keep everything exactly the same, U infinity, T infinity, the surface temperature is the same. But if I take this same surface and I turn it so that it is perpendicular to the flow, that's a geometry, that would be considered a geometry change, and the average heat transfer coefficient over this surface to facilitate a heat flux or a heat transfer rate by convection is going to be different. So even if the temperatures of the fluid and the surface are the same, by changing the geometry, such that here the change in geometry is just the change in the orientation of that same surface to the fluid flow, I'll get a different value for the heat transfer coefficient. And so this the dependencies on the fluid properties, or the dependence of the heat transfer coefficient on fluid properties, fluid velocity, and surface roughness all have to be considered, in addition to finally the type of fluid flow. And we only use really two types for flow over a flat plate. The flow types that we'll consider come from the hydrodynamics of the problem, which is laminar and turbulent, or let's say laminar or turbulent flows. So all of these considerations go into the calculation of the heat transfer coefficient, in that heat transfer coefficient is that, this what we multiply the temperature difference by in order to get the expression of a heat flux. And so when we're considering, well, how do you get to a calculated value of the heat transfer coefficient? Thus far, the heat transfer coefficient has just been given as a part of a problem statement. Or if you have other quantities, you might be able to solve for the value of the heat transfer coefficient. But at this point in chapters 6, 7, 8, 9, and 10, all of those chapters of this textbook are devoted to how we determine heat transfer coefficients associated with a convective flow, such that if the conditions of the flow, fluid properties, fluid velocity, the surface or things about the surface like the geometry and the roughness and what type of flow is present, correlations are presented on how to actually calculate the heat transfer coefficient with the knowledge of these quantities, so that we can then use that heat transfer coefficient to calculate the convection heat flux or the convection heat transfer rate. Now, on a microscopic basis, when I talk here about that no-slip condition, the no-slip condition gives us a starting point from which to start to develop some expressions for heat transfer coefficients and consider qualitatively what is that heat transfer coefficient representative of. So if I take and just kind of blow this up here, if I have a stationary set of molecules on the top of this surface, and I go back and let's say this is this surface temperature Ts, and I have a fluid free stream velocity and a fluid free stream temperature U infinity and T infinity. Well, we know that if Ts is greater than T infinity, there will be some heat transfer rate by convection through this surface. But through this stationary set of molecules that I've drawn here, because they're not moving, that heat transfer rate by convection that moves from the surface into the fluid also has to be equal to the heat transfer rate by conduction just through this stationary set of molecules. So basically what this says is that the heat transfer rate by convection that occurs from the surface into the fluid must be equal to the heat transfer rate by conduction that's occurring through the stationary set of molecules. Now here, the heat transfer rate by convection will be the heat transfer coefficient times Ts minus T infinity times the surface area, and the heat transfer rate by conduction will be minus K dt dy, and this is at y equals 0 times the same surface area. So here the coordinate system is positive y from that surface in the upward direction and positive x from left to right. Now the heat transfer rate we consider to be perpendicular to the plate, so that would be in the y direction. So we're considering dt dy at y equals 0. Now this K, since we're talking about heat transfer rate by conduction through the molecules, this minus K is the thermal conductivity of the fluid, not the solid surface that the plate is made of, because this is a heat transfer rate by convection is equal to the heat transfer rate by conduction through the stationary set of molecules. So when defining this heat transfer rate by conduction through those molecules, it's the thermal conductivity of the fluid. And this temperature gradient is a temperature gradient that is in the fluid. And that there's a temperature difference that is required to support the heat transfer rate by convection, and there's also a temperature difference required to support the heat transfer rate by conduction through that stationary set of molecules. Now, the surface areas used to define the convection and the conduction are the same. So this is just really an expression of an equating of the heat flux by convection to the heat flux by conduction. If I take this expression and isolate for the heat transfer coefficient, it says the heat transfer coefficient is minus K of the fluid times dt dy evaluated at y equals 0 divided by Ts minus T infinity. So now, just to go back a second, the dt dy at 0, that's at y equals 0. So y equals 0 is at the surface of the plate. So that's an indication of the temperature. We're talking about specifically the temperature gradient at y equals 0, which would be through those stationary molecules, because as we move up and away from this surface, the temperature gradient is going to become less and less as we move in the y direction, such that once we're outside of what is called the thermal boundary layer, dt dy will be equal to 0, because outside that thermal boundary layer, the temperature everywhere in the fluid will be just the free stream temperature, that is T infinity. So we have to be very specific when we're writing this equality of what's happening right at the surface of this plate here. So we can define the heat transfer coefficient as the negative of the thermal conductivity of the fluid times the temperature gradient in the fluid at y equals 0 divided by the surface temperature minus the ambient temperature. In the units here are watts per meter squared Kelvin or watt per meter squared degree C. But this becomes that expression. Now, the thermal conductivity of the fluid, we're typically going to just take at an average temperature, and we would define what that, or what's called a film temperature, which is just the average temperature between the surface and the free stream temperature. But this temperature gradient, dt dy, this actually changes as we move along the length of the plate. So even if the surface temperature and the ambient temperature are considered to be constants, dt dy, the temperature gradient in the fluid, will change as we move in the x direction. And this is the reason that this heat transfer coefficient actually varies as a function of position. Now, we've used what are called average heat transfer coefficients over a plate or over a given surface. So when there was one value given in previous problems where we considered convection, that heat transfer coefficient is actually described as an average heat transfer coefficient only because H varies with position. So that if I was considering a plate with my coordinate system drawn here in the positive y and the positive x here, if fluid is flowing over this surface with a free stream velocity and a free stream temperature, the heat transfer coefficient that would exist over this plate actually varies as I move from x equals 0 to x equals L. So if the heat transfer coefficient varies here in the x direction along the length of the plate, we would have to consider that if I wanted to calculate the total heat transfer rate from this plate, I would have to integrate along the length of the plate in terms of a heat transfer coefficient that varies as a function of position. Or if I wanted to draw this plate so that here I'm considering with a similar set of or a similar coordinate system. Here, the y direction is upward away from the plate. Here's the x direction, and here is the z direction. We'll actually make it in opposite direction. So stick with the positive right-hand rule here. But if I move along the length of this plate, if I have the same fluid, U infinity, T infinity, so that now I'm considering there's a surface temperature and there's a surface area here. So if the air or the fluid is moving in the x direction, or it could have an X and a Z component, I would expect that there would be a temperature variation over, a heat transfer coefficient variation over this entire surface for this given surface temperature. When a single value of the heat transfer coefficient is given, whether we're only considering variations in the X or variations here in the X and the Z directions in this over this surface, an average heat transfer coefficient can be defined just by integrating over the area or the length where the heat transfer coefficient is actually varying. So for here, for this plate, where we're only considering variation that might occur in the X direction, here the average heat transfer coefficient would just be equal to the integral from 0 to L of the local values of the heat transfer coefficient, dx, times 1 over L. So this would just give me an average expression of the heat transfer coefficient when the heat transfer coefficient varies in the X direction from X equals 0 to X equals L. Thus, we define the bounds, and then we divide by the length. Well, we define bounds for integration of this local value over the heat transfer coefficient, and we divide by the length over which we integrate it, and that'll give us an average heat transfer coefficient from 0 to L. If we were considering an area over which that heat transfer coefficient could vary, here H average would be defined as the integral just over the surface area, which would be in the X and in the negative Z directions according to the expression I've given. So let's see here, if I write this, this is 0 to L in the X direction, and here in the minus Z direction. I'll call it, let's say W, for the length and the width of this plate. So if I integrate over the surface area, the expression of the local heat transfer coefficients, DAS, and then divide by the surface area, that'll give me the average value here. So if I wanted to make this expression explicit, instead of just generally writing this as the integral over the surface area, here since I've indicated the positive X and the negative Z directions here with constraints in the X and Z directions, this expression will be just written as the integral from 0 to L through the X direction, and the integral from 0 here, because I've written this as the positive Z from the coordinates, so this would be to negative W, the local heat transfer coefficients, dz dx times 1 over the surface area. Well, the surface area here is L by W. So that's how, for this specific case, where I've indicated bounds in the X and the Z directions. And here I'm integrating through the X and Z directions because that's the plane in which this surface is lying, in that the positive Y is up and away from the surface. This is how I would get the average value of the heat transfer coefficient. So here, these two expressions are just general expressions on how we would calculate the average heat transfer coefficient that exists over a given surface. So if I wanted to consider, well, what is the heat transfer rate by convection from, let's say, this surface? Well, the heat transfer rate by convection, again, is just the heat transfer coefficient times Ts minus T infinity times the surface area. So here the surface area would be L by W. The temperature difference would just be Ts minus T infinity, and the heat transfer coefficient would have to come from an expression of the integral over the surface area of the local heat transfer coefficients, and then divide by the surface area. So this just means that the expression of the local heat transfer coefficient has to be written in terms of X and Z in order to perform this integration. Now, if it was a constant, it would just come out, and I would end up with an expression of the heat transfer coefficient that is just, if it's an average value, it's just going to be an average value, and that it's not a function of X or Z. But if it is a function of X or Z, we'd have to go through the expression of the heat transfer, or an expression of the integration based on what the dependency of the local heat transfer coefficient is. In this case, where the local heat transfer coefficient would only be a function of X, we would substitute in that expression and integrate it so that we can then divide by the length over which we integrate it, and that will give us the average heat transfer coefficient. So when we're talking about an expression of a heat transfer coefficient, it's always with consideration that the heat transfer coefficient varies with position. And you would have to imagine that that would be so, because if I have fluid moving over this surface and heat is being transferred into the fluid, well, that actually slightly changes the temperature of the fluid so that it's picking up heat as it's moving along the length. Now, it won't change the free stream temperature, but if you imagine a layer over this surface where the temperature is changing, that's what we call a thermal boundary layer. Just like we have a velocity boundary layer, and that a velocity boundary layer says that there is a free stream velocity, but right next to the surface, because of the no slip condition, we have a layer of molecules that have a zero velocity. And as I move up and away from that surface, the velocity varies between 0 and U infinity, and that we would use that to define a velocity boundary layer. Well, in heat transfer, or for the heat transfer problem, we would define what's called a thermal boundary layer, where the temperature varies between Ts and T infinity. So if the fluid temperature is varying as a function of position because heat is being transferred into the fluid, then the thermal conductivity of the fluid, which is a function of temperature, would change. Just the heat transfer coefficient will change. Here, the temperature gradient changes because if the thermal boundary layer is growing as it moves along the surface of this plate, then this is an expression of the change in temperature with respect to Y at this position. Well, if the thermal boundary layer is growing, and I'll go to some pictures of these in a second, or drawings. If this temperature gradient changes, then H changes, whether the thermal conductivity is changing or not. So if the heat transfer coefficient varies as a function of X, then we have to just integrate in order to find the average value. Or if the temperature variation in dt dy varies as a function of X and Z, we have to integrate through X and Z in order to get a value of the average. And we'll get more into the depth of the correlations that are going to be associated with how you actually calculate these quantities. But before we get into that, because those correlations are for multiple fluids, for multiple velocities, and sets of conditions, the use of dimensionless parameters or dimensionless quantity, what we also call them dimensionless numbers, are determined so that we can write expressions for heat transfer coefficients that cover multiple fluids under multiple for multiple velocities. One of these quantities that we use to describe convection and actually to represent the physical mechanism associated with convection, represent of convection here. One of those is what is called the Nusselt number. Now, this is a very important number for heat transfer, in that most of the correlations that are presented for the determination of a heat transfer coefficient are going to be presented as expressions of Nusselt numbers. And the Nusselt number is what we call a dimensionless convection heat transfer coefficient. Here, H dot T dot is just short for heat transfer coefficient, or heat transfer. A dimensionless heat transfer coefficient. This expression is often thought of as a ratio of pure convection to pure conduction that would be occurring inside of the or in the fluid. So the Nusselt number is shorthanded as a capital NU, and it's defined as the heat transfer coefficient times the characteristic length divided by the thermal conductivity. Now, if you recall from chapter 4, when we were using lumped capacitance for transient analysis of temperatures in objects where we could consider the temperature to be uniform, we had a definition of the BO number as the heat transfer coefficient times the characteristic length, which we defined as the volume divided by the surface area divided by the thermal conductivity. So the Nusselt number has the same form, except the key difference here, I mean, it's still a convective heat transfer coefficient, a characteristic length, but the characteristic length is not going to be defined as a volume over a surface area, but it is a length that we'll consider divided by K. Now, for the BO number, the thermal conductivity was the thermal conductivity of the solid material, because we were looking for BO numbers to be less than 0.1, which just says that the temperature gradients inside the object were negligible. Here, the Nusselt number uses a similar representation of a heat transfer coefficient times the characteristic length divided by thermal conductivity, but this thermal conductivity is the thermal conductivity of the fluid. So here, sometimes you'll see K sub F, where K sub F is just the fluid thermal conductivity. And the reason the thermal conductivity of the fluid is used in the definition of the Nusselt number is that when we consider a fluid flowing over a plate, there will be a thermal boundary layer that will grow, and we'll call this delta sub T. And this, in this thermal boundary layer is actually where all the heat transfer occurs. Once we get outside the thermal boundary layer, the temperature in the fluid is uniform, whatever the free stream temperature is. So once we get out here, there's no more temperature difference between a joint molecule, so there's no more heat transfer occurring. Inside this thermal boundary layer is where we have all the temperature variation, such that the temperatures that exist in the fluid are between the surface temperature Ts and the free stream temperature that is T infinity. This expression of the thermal conductivity is used to describe the heat transfer that will be occurring by conduction inside this thermal boundary layer, which would be in those stationary molecules at the very bottom here. The rest of I said very bottom. The very bottom is the that's the stationary set of molecules that are touching the surface. The heat transfer coefficient is associated with that heat transfer that will be occurring in the molecules that are actually moving. So right above that first layer of molecules, right on the surface, all the other molecules move. And when they move, that's where we get the heat transfer by convection occurring. So this Nusselt number is actually, describing heat transfer that occurs by convection inside this thermal boundary layer and conduction inside the thermal boundary layer. So that this expression of the Nusselt number is a dimensionless parameter, has no units associated with it. H times L sub C. This would be watts per meter squared times meters, which would give us watts per meter Kelvin, which is the same units as thermal conductivity, watts per meter Kelvin. So this is a unitless parameter, but this expression of the Nusselt number is one that is going to primarily be used in order to write an expression for a heat transfer coefficient. So if I rearrange this expression, I can write that the heat transfer coefficient H will just be the thermal conductivity of the fluid divided by L sub C times the Nusselt number. So that if the Nusselt number is defined according to some correlation, it says that I will be able to take the thermal conductivity of that fluid divided by whatever the characteristic length is and multiply by that correlation that is used to define the Nusselt number to then get the heat transfer coefficient. In the definition of this Nusselt number is where we'll take into account things like the fluid properties, the fluid velocity, the surface geometry, and the flow type. All of those dependencies will be wrapped up in the definition of the Nusselt number so that we can multiply by the ratio of the thermal conductivity to the characteristic length. That will give us the value of the heat transfer coefficient that we should actually use. Now, when we start talking about, well, what are the things that go into this expression of the Nusselt number? Well, we'll talk about classifications of the fluid flow, or let's say types of, well, I guess I'll say classifications, because there are multiple things that are considered in order to write expressions and select, write expressions that we won't actually, well, there are multiple considerations for the grouping of expressions based on the classification of the fluid flow. Now, much of this has to do with the hydrodynamics, which was covered in fluid systems. We'll consider, well, is the flow viscous or inviscid? If the fluid is viscous, that means we're going to have a velocity boundary layer that will exist due to that no-slip condition. If it's inviscid, that means that if it's an inviscid flow, it just means that there's no shear stress to be considered. If there's no shear stress to be considered, all of the shear stress starts at the place where we have a no-slip condition. So if it's an inviscid, that just says that there won't be a boundary layer to actually consider in the flow, and thus a velocity boundary layer, and thus the non-existence of a velocity boundary layer has a significant effect on what the thermal boundary layer would be in a problem, and thus it would affect the construction of a correlation used to define a Nusselt number to eventually be able to calculate a heat transfer coefficient. So we, when we're considering the fluid flow, this is a consideration for the combination of the conditions and the type of fluid that we're using. And the reason I say is considered based on the conditions. If I have a slow moving air over a surface, often we would consider that to be an inviscid flow. But as we increase the velocity of the air moving over a surface, we may not be able to ignore the fact that there is a no-slip condition, and there's going to be a significant velocity variation from the surface into the fluid, and thus we would have to consider it to be a viscous flow rather than an inviscid flow if the fluid was moving, if the air was moving really slowly. If we're using oil, no matter how slowly we move oil, because the fluid is so, by the fluid properties, it's so viscous, we would always have to consider it to be a viscous flow and not an inviscid flow because the viscosity is so high. When air, which has a very low viscosity, if the velocity is low, we could often consider to be inviscid flow. But as we increase the velocity, the existence of a viscosity does then start to make it a viscous flow if the velocity is high enough to consider it, to consider those viscous effects. Now, we also consider, is it an external or internal flow? Now, external is something like a flow over a flat plate. You'll know it's always going to be considered an external flow if there's a definition of a free stream velocity. If at some point as we move away from the surface of interest, if the velocity of the fluid becomes uniform and thus is unaffected by the presence of the solid surface where heat transfer is occurring, we would consider that to be an external flow. An internal flow is one where the fluid is actually confined. Internal flow would be like flow through a pipe. If I have some mass flow rate through a pipe, this is what we call an internal flow, in that the fluid is not able to just eventually get to some free stream velocity. There's a velocity associated with the fluid, such as if I have a mass flow rate, and the mass flow rate is the density times the cross-sectional area of the pipe times the velocity. Well, if the pipe diameter is constant, then the cross-sectional area is constant. If the density is constant, then it says that the velocity would be constant along the length of the plate, or along the length of the tube or the ductwork here. But in that internal flow, the fluid is actually bound by the duct that it's flowing through. In an external flow, the fluid is not bounded, so that if I move far enough away from that surface, the fluid is not affected by the presence of that object in the fluid itself. We could also consider, for the fluid flow, is the fluid compressible or incompressible? This will affect also the heat transfer coefficient. Now, that it has nothing to do with the temperatures, but it does have to do with the density of the fluid. Such that, recall that the density times the specific heat of the fluid is an indication of the amount of energy that can be stored in the fluid. That stored energy results in a temperature. And if I change the density of the fluid as it's flowing over a plate or through some ductwork, then that will affect eventually what the heat transfer coefficient would be that we would actually define. Now, of course, we also have to consider, is it a laminar or turbulent flow? Those are the two major designations for fluid flow types when we were considering just the fluid dynamics of the problem, such as the surface temperature, the fluid temperature were the same. We evaluate the properties at one of those temperatures because they were the same. And we would consider, is it a laminar flow, where in the laminar flow, it's dominated by viscous forces, and the turbulent flow is dominated by inertial forces, and we would use the Reynolds number, where that Reynolds number, once it reached a threshold value, we would consider it to become turbulent, where at the lower values it's laminar, and because for certain sets of conditions, the fluid can be considered not all laminar, well, not laminar and not quite fully turbulent. We consider it also to be what's called transitional. And that transitional just says that it the fluid flow can alternate between having characteristics of a laminar flow and of a turbulent flow. For our calculations, we're only going to consider it to be laminar or turbulent, just based on the calculation of a Reynolds number. And then, of course, going back to what I was considering before, is this a forced or free convection. That has to do here, forced or natural and free convection are actually interchangeably used. So here, free/natural. Again, the forced convection just says I'm using some external means to move the fluid or to impart inertia to the fluid. So that's usually a fan. We could consider wind to be used to force, let's say, air. If it's free, that just means that there's no wind blowing, there's no fan blowing, but the air starts to move in the opposite direction of the gravitational field, so upward, due to buoyancy forces that are exerted on the fluid by the surrounding colder or cooler molecules. And we also have steady or unsteady flows. Now that has to is the consideration of steady. Just says that if we're talking about a steady flow with regard to the velocity, it says the velocity is not changing with respect to time anywhere. Or in our case, if we're doing a thermal analysis, the temperature of the fluid can vary throughout as a function of position, but the temperature is not varying as a function of time when it's steady. And if it's unsteady, it's just the opposite of that. It just means that the temperature does vary as a function of time, or the velocity does vary as a function of time. Now, if we say it's uniform, uniform just says the temperature everywhere with respect to position would be the same, or velocity would be everywhere the same. It's not zero. It just is it just is the same when we say it's a uniform condition. We also have, for the classification of the flow, is it 1D, 2D, or 3D? Meaning, does the temperature vary as a function, let's say, of just X, as a function of X and Y, or function of X, Y, and Z? So going back to here, this is what we call flow over flat plate in one dimensional, in that here I consider that the heat transfer coefficient only varies as a function of X. And thus we could only consider the velocity changing as a function of X, or the temperature changing as a function of X. In this condition here, where or this situation I drew here, where we consider a flat plate that had a surface area over it, here we consider that the heat transfer coefficient can vary as a function of X and as a function of Z over the plate. So that would be considered a two-dimensional flow. Or in the case of, let's say, something like a flat plate, where the fluid temperature varied in the fluid. So let's say if the temperature of the fluid varies in the X direction and in the Y direction here, that would be a two-dimensional flow, because depending on what value of X and Y, as I move along the length of the plate, that would be a 2D flow. And it would be 3D if I consider that if I move in the X, Y, and in the Z direction, the temperature vary as a function of all three. So the complexity increases, but 1, 2, and 3D flow just have to do with, does the temperature or the velocity of the fluid change as I move in each of the coordinate directions used to define that flow. Now, I actually want to go to some of the figures that I pulled out of the text for some of these other expressions here. Here, this first expression, this is for what we call duct flow or pipe flow. And you should remember this from fluid systems, but this is just an expression of the hydrodynamics of the problem. If we have fluid entering a pipe, it enters with we usually consider to have a uniform velocity initially. And then that velocity starts to change, that velocity distribution changes due to the no-slip condition. Here that at X, or here this is in the R direction for a pipe flow. So here, this is R equals 0. And here, this is R equals capital R for the radius of the pipe. So at the radius of the pipe, we'd have that no-slip condition that would start to take an effect inside the pipe, such that the velocity is 0 at R equals capital R. And this happens all around the inside of the pipe, along the inside perimeter of the pipe. And so it starts to slow down the molecules right next to the surface. Well, we also know that for steady flow, the mass flow rate is the density times the cross-sectional area times the velocity. Now, this velocity is the average velocity through the fluid or through the pipe. So if the mass flow rate stays a constant, and V average, if I just rearrange this expression, say m dot over rho AC, if the mass flow rate is a constant and that the rate at which mass enters and leaves the pipe is the same, the density, if it's considered to be an incompressible substance, the density stays the same. And if the pipe has a constant cross-sectional area, A sub C is the same. So that says that the average velocity is the same all along the entire length, but the average velocity is the average velocity at any point. So notice here, if I take the point here and the point here, there are different velocity distributions. The velocity is 0 at R equals capital R, and the shape is different for each one for these two positions, and I'll call this position 1 and position 2 here. At position number 1, there's a distribution such that there across the center line of the pipe, we have an area here where the velocity is uniform around the center line of the pipe. And when you get out to here, there's basically like one position at which the velocity is maximum. Here I have an area where the velocity is maximum. That's because the average velocity here at position 2 and the average velocity here at position 1 have to be exactly the same for a steady flow condition, but the distribution of the velocity can change. In the average velocity at either of these points 1 and 2, that's the average velocity over the cross-sectional area of the pipe, so that the distribution of the velocity can change, but the average velocity of that distributed velocity throughout the cross-sectional area has to be the same to just satisfy conservation of mass for steady flow conditions. Here we have the existence of what's called an inviscid core, this blue line here that grows together from the perimeter or the radius of the pipe towards the center line. This inviscid core is just a place where viscous effects have not yet been taken into account, or they haven't affected the flow. But once they grow together, this is what we call the hydrodynamically fully developed condition. In fluid systems, this was probably referred to as just fully developed because there's only one fully developed to refer to. When we talk about heat transfer, we have to differentiate between hydrodynamically fully developed and thermally fully developed. So we won't just use fully developed as a description because we have two fully developed conditions. So we consider this to be the inlet of the pipe to the point at which this blue line is actually the velocity boundary layer that grows together to the center line of the pipe. But as it's growing, this is what will be called the hydrodynamically developing region. And from that point on will be the hydrodynamically fully developed region. And the consequence of hydrodynamically fully developed just means that the pressure drop as a function of position, dP dx, becomes a constant. Whereas in the hydrodynamically developing region, dP dx changes as a function of position. So this this hydrodynamic part of the problem will affect, particularly here, this is for an internal flow where it's flow through a pipe. When we look at expressions for heat transfer coefficients or expressions for Nusselt numbers that we use to get heat transfer coefficients, the consideration of is it hydrodynamically developing or hydrodynamically fully developed will be a consideration for the correlations that we would select to get a heat transfer coefficient. Now, this is also another familiar expression of the laminar and turbulent boundary layers that exist for the hydrodynamic problem, in that this laminar boundary layer, or in the laminar region, when we have this boundary layer that's growing, this is the area where viscous forces dominate. In the turbulent condition or the turbulent flow condition, this is where inertial forces dominate. And so there is a transition region where the fluid is not behaving in a laminar way and not fully turbulent. This transition region, we actually will reduce all the way down to a transition point, as was also done in fluid systems. So that here we have this region that extends from here to here that breaks the laminar and the turbulent regions, but we'll take this all the way down to a transition point so that we won't consider a fluid flow that is in what we call to be transition. We would consider it to be either laminar or turbulent because we've reduced the transition region down to a transition point. And that transition point is, it just becomes the point at which the fluid is no longer laminar, but we consider it to be turbulent. And that's just to simplify the selection process for a correlation based on a laminar or a turbulent flow condition. Now here is velocity distributions. Notice here the shapes. When we're calculating, let's say, a shear stress, let's say to calculate the force of drag that will be operating on this surface where this boundary layer is forming. The shear stress, tau, is defined as the dynamic viscosity, mu, times du dy. Du dy is a change in the x component of velocity as I move in the y direction. So here this lowercase u is just the velocity in the x direction. A lowercase v is the velocity in the y direction. So as the velocity in the x direction changes as I move through y, so that's just as I move up in the y direction, here see, it's not drawn. Here's a coordinate system here, positive y and positive x. So as I move in the y direction and consider the u component of velocity, which is just in the x direction, we can calculate this shear stress. Well, if I want shear stress at the wall, tau sub w, to calculate the force of drag acting on that surface where the fluid is flowing over it, this is mu times du dy evaluated at y equals 0. So right at this surface, du dy is the velocity gradient that we can draw right here and right here. These velocity gradients is what gives us an expression of the wall shear stress that changes as a function of position. So if you recall back to some of the calculations that you may have made, you can calculate expressions of local shear stress on the wall and average values of the shear stress on the wall. And the average values are because the shear stress varies as a function of position along the length of the plate. And the reason that shear stress varies as a function of position is because du dy, the velocity gradient at y equals 0, varies as a function of position. So when we're considering the expressions of shear stress varying as a function of position due to velocity gradient variations. Expressions of the heat transfer coefficient will also vary as a function of position. Now, just again, as review, this red line that was drawn as the boundary layer, this is what we call the velocity boundary layer, delta. And that is in contrast to delta sub T, which is the thermal boundary layer. Both of those layers we will be concerned about. The velocity boundary layer is just a place where the velocity varies between 0 on the surface due to the no-slip condition to here V, which is the free stream velocity of the fluid. So inside this boundary layer is where we have all of inside the velocity boundary layer is where we have all of the variation of the velocity in the fluid, because outside of the velocity boundary layer, the velocity is everywhere V, or the free stream velocity. And so this line is defined where the velocity in the fluid, U, becomes 99% of the free stream velocity. So when we consider, well, where is it? Delta is defined where U is equal to 0.99 of V, where V is the free stream velocity. So that is, so if we were measuring or calculating, well, what is the velocity in the U direction? If the velocity was 1 meter per second, as we move up in the, well, actually probably easier here. Let's say if V, let's say is equal to 1 meter per second. Here at Y equals 0, this is the Y direction. At Y equals 0, due to the no slip condition, the velocity is 0. As I move in the upward in the positive Y direction, the velocity will increase according to this line here. And once it gets to, let's say, according to what's drawn here, this is delta. When we get to this point here, U would be equal to 0.99 meters per second. And that's where we would define the boundary layer, the velocity boundary layer, to actually exist in the fluid. So that when we're considering expressions for where that velocity boundary layer exists, that's the consideration that's made for writing or drawing a representation of that line there, is that it's just an expression of the place where the velocity inside the boundary layer now becomes 99% of what the free stream velocity is. So that's where we can say, okay, everywhere below that line, the velocity is less than the velocity that is the free stream velocity, and its lowest value is 0 due to the no slip condition at Y equals 0. Now we also have what's called the thermal boundary layer. So here, see, this is delta sub T, but often we just write it at the end. So along this line is what we call the thermal boundary layer. And in here is where all the temperature variation occurs. Outside the boundary layer, the temperature is the free stream temperature, that is T infinity. Right along this surface, temperature of the fluid is the same as the surface temperature. So that everywhere in between, in this green area, the temperature is lower than the free stream temperature, and also higher than the free stream temperature if Ts is greater than the, if the heat transfers from the surface into the fluid. And actually in this problem, this here, Ts, just to make sure I go along with the schematic that's provided here, Ts is less than T infinity. So that just says that the heat transfers from the fluid into the plate. How do I know that? Well, look here. Here's the magnitude of T infinity by the length of this line. Here's the magnitude of TS. So this is TS is less than T infinity. So the heat transfer would just be into the surface, from the fluid into the surface. And we have problems like that, but we still have the existence of a thermal boundary layer. In this problem, inside the thermal boundary layer, in this green area, the temperature is less than the ambient temperature. And its lowest value is the surface temperature, with this variation of the surface temperature indicated by the lengths of each of these orange lines. So when we're drawing thermal boundary layers, there are no arrows here because there's no direction associated with temperature. The length of these lines is an indication of the magnitude, whereas in the velocity boundary layer, we do have these arrows to indicate the magnitude of the velocity of the velocity of the fluid with the direction included. So here, this expression is going to be defined, this expression of the thermal boundary layer is going to be defined as the position at which there is that 99% of the temperature difference occurs. So here, what we're looking for is, this is delta T is defined where the temperature in the fluid, so here I'll just write T minus the surface temperature divided by, well, I'll say it's equal to 0.99 of T infinity minus the surface temperature. So here, if T infinity, let's say if I make this, I don't know, let's say I'll make this 100 degrees as the ambient air temperature that's applying heat to a surface that is at 10 degrees. So the temperature difference here is 90 degrees, right? So this is 0.99 times 100 minus 10 here. And here, this is T minus the surface temperature here will be 10 degrees. So when the temperature minus the surface temperature, now this is the temperature in the fluid here, is equal to 99% of 100 minus 10, which is just the temperature difference. So that's basically the temperature, whatever this temperature is, minus the surface temperature. When that temperature difference, and when 99% of that temperature difference is equal to the temperature difference between a position in the fluid minus the surface temperature, that's when we say we're at the position that defines the thermal boundary layer. So it's a little bit different expression because we know that due to the no-slip condition, the velocity is always just a zero here. And that there's a fluid velocity, that's the free stream velocity, that's a constant. It's basically exactly the same equations, except that we're taking into account that the surface temperature is zero. If we let the surface temperature be zero, this becomes T is equal to 0.99 of T infinity, if Ts is equal to zero. And the equation will look exactly the same as the velocity is equal to 99% of the free stream velocity. But because the surface temperature is often not 0 degrees, the definition of where the thermal boundary layer exists has to take into account of a temperature difference. There's a temperature difference between the fluid and the surface, such that when 99% of that temperature difference is reached, that's when we consider that's where the thermal boundary layer exists. Again, inside the thermal boundary layer is where all the temperature variation occurs. Outside, the temperature is uniform at just the free stream temperature. So these are considerations of the physical quantities that are associated with with heat transfer analyses. We have to take these into account because the heat transfer coefficient is just that. It's a coefficient, not a property. So we also define a relationship between the thermal boundary layer and the hydrodynamic or the velocity boundary layer. So there's a relationship such that delta and delta sub t are related through what is called the Prandtl number, Prandtl. And it's another dimensionless quantity, PR, and it is defined as the kinematic viscosity nu divided by the thermal diffusivity alpha. Now, this can also be written as the dynamic viscosity times the specific heat over the thermal conductivity of the fluid. And this Prandtl number is the molecular, it's a rate of molecular diffusivity of momentum, or we'll just say momentum diffusivity to thermal diffusivity. How well does it diffuse momentum to how well does it diffuse thermal energy? And so those are those two quantities of the momentum diffusivity and the thermal diffusivity are the direct result of what's happening to form a velocity boundary layer and a thermal boundary layer. Such that what we'll find is that for Prandtl numbers, or for fluids that dissipate heat very well, we'll have Prandtl numbers that are much less than the value of 1. Fluids that, let's say, I'll say dissipate, well, I'll keep it the same, dissipate heat slowly. We'll have Prandtl numbers that are much greater than 1. So like liquid metals. Liquid metals typically have values that are less than 0.1. Gases have values that are closer to a value of 1. But things like oils, whether they be engine oil or glycerin, have values that are many times greater than 1, and that they diffuse momentum very well, but they don't diffuse heat very well. This Prandtl number is a ratio, can be considered as a ratio of momentum diffusivity to thermal diffusivity. So according to this ratio, the higher the thermal diffusivity, the lower the value will be. So for, again, things like liquid metals and gases, they dissipate or diffuse thermal energy much better than they dissipate or diffuse momentum. Really thick fluids are going to dissipate momentum much better than they dissipate or diffuse thermal energy. So we'll use that Prandtl number, and depending on the type of flow, the relationship between the thermal boundary layer and the velocity boundary layer are going to be different, but they'll be related through the expression of this Prandtl number. And of course, the last dimensionless parameter that we want to consider for any types of fluid flow or convection is the Reynolds number. And that Reynolds number is the same expression that we've used before. It will be considered the velocity times a characteristic length. Let me write this. There's two ways around. Well, I'll consider the velocity times the characteristic length over the kinematic viscosity, or the density times the velocity times the characteristic length divided by the dynamic viscosity, such that the kinematic viscosity nu is just the dynamic divided by the density. This expression for the Reynolds number, for low Reynolds numbers, it just says that the fluid flow is dominated by viscous forces. And for high ones, it's dominated by inertial forces. So this is often referred to as a ratio of inertial forces in the fluid to viscous forces in the fluid. And depending on the flow configuration, the way that we define that Reynolds number will be different. We have Reynolds numbers that we can define with a characteristic length that'll be the length for flow over a flat plate. But the characteristic length, let's say for a sphere or a cylinder, would be its diameter. And depending on the kind of the kind of calculation you're making, it may be a local value, well, a Reynolds number based on local calculated for the determination, something like a local heat transfer coefficient, or for an average heat transfer coefficient. These expressions that we consider are ones that, or these expressions based on the Reynolds number allow us to consider things like, do we need local values or do we need average values? And the correlations that we'll reference for those heat transfer coefficients will require that we calculate the Reynolds number in a specific way so that we can express exactly what those quantities are for a given expression that would exist for a given set of conditions. And so to kind of demonstrate that, we can look at how we would solve problems, and we'll get into, particularly in chapter 7, what are the very specific correlations that we would use in order to make those calculations, because those calculations are not, they're not as easy as just reading a heat transfer coefficient from a problem statement. Here, we're going to take into consideration these quantities or these considerations of, let's see, what was it? Yeah, these classifications of the fluid flow, along with these considerations of all the fluid properties, the velocity, the geometry of the surface, and the flow time. So we have to take those things in, or make those considerations, and so that we can actually calculate or select the right correlation to make the calculation of a heat transfer coefficient. Now, just to kind of put together some of these principles or concepts, we will consider a problem that has a combined convection and conduction that occurs. So let's say we have a plate that is cooled by moving air. So I have this plate, and this plate is made of a material with a given thermal conductivity. And the air that is moving over the upper and the lower surfaces of this plate. So basically there's consider that the air is moving over the top and the bottom of the plate, so that the plate has a measured temperatures, a T1 and a T2. So these are actually measured quantities, and the ambient temperature of the fluid is also being measured. And so we want to consider, well, what must the heat transfer coefficient be based on these quantities that are specified? What are the heat transfer coefficients in the air? Now here, the heat transfer coefficient, now we can have well, I actually want to say, well, I'm going to say heat transfer coefficient because I have to specify some quantities here in order for us to get to this. So I'll say here that T1, the temperature on the top of the plate is 60 degrees and T2 is 120 degrees here. The temperature of the fluid is 20 degrees and the thermal conductivity of the plate is 200 watts per meter Kelvin here. Now, the surfaces of the fluid, or the surfaces of the plate exposed to the fluid are both higher than the ambient temperature or the free stream temperature of the fluid. So that means that I'd have heat transfer out of the plate into the fluid as it's moving around this plate. So there'll be heat transfer out, out of the plate. And the expression of the transfer that's occurring, actually, for this problem, it's actually for what I want to calculate. Because yeah, this is another variation I want to consider for this problem. Let me modify this a little because this is a more advanced problem that I want to solve. Instead of the fluid flowing across the top and bottom, it's just going to flow across the top portion here. And we'll look at the other problem later. So what is the heat transfer coefficient in the air? And here, air flows over the top of the plate. And we'll look at both sides later because it's just a little bit more complex. So if the heat or if the convection or if the air can only flow over the top of the plate, then convection is only going to occur on the top of the plate. So if I have convection occurring on the top of the plate, then that heat that is convected away, in order for this to be a constant, for these to be constant temperatures, T1, T infinity, that means then that heat has to be supplied to that same surface, and that will be supplied by conduction. So here, the heat that is moving away from that surface must be equal to the heat that's moving to that surface. The heat transfer rate by convection will be H times, here this would be T1 minus T infinity, because that's the surface that's exposed for convection. And the heat transfer times A. And the heat transfer rate by conduction would be from the surface that is a temperature T2 to the surface at T1. So this would be K, or we can write this as minus K dt dy times the surface area. Here this is where I consider the y direction here. So that to make this, and this is a heat flux times the surface area, where this heat flux is by conduction. So this would be minus K times the temperature at position number 2, which would be T1 minus T2, divided here by the thickness of the plate. And actually, I didn't write the thickness of the plate. Let me see that. see the thickness of this plate here, we'll call L. So that L here, let's say, is a large temperature. Let's say make this 10 centimeters here. So when writing this expression, this temperature difference over a distance of L allows me to define the temperature gradient times here the surface area. Now here I don't need to specify the surface area to find the heat transfer coefficient, but here this surface areas will cancel. And this says that the heat transfer coefficient will be minus K, T1 minus T2 divided by L, divided here by T1 minus T infinity. So here with the thermal conductivity, the temperatures, and the thickness provided, we can find the heat transfer coefficient. This is just based on conservation of energy applied at this surface here. So that if I wanted to use this heat transfer coefficient as the average heat transfer coefficient across the surface, I could also calculate the temperature gradient in the fluid, and I'm already 1 minute over, so we'll stop right here. But the basic principles or the concepts of the heat transfer by convection being related to the heat transfer by conduction in the surface is one that we've used before, but we'll extend this and consider that there is also a stationary set of molecules right across the top. So I could also consider how we would solve for the temperature gradient that's in the fluid right next to this solid surface that would exist in the fluid here. So we'll pick up here the next time and get into many of the correlations that we'll use to actually calculate the heat transfer coefficient, not based on just an energy balance, but based on correlations that define, well, what is the fluid type, what is the flow type, et cetera, so that we can use those correlations to calculate heat transfer rates. All right, that's it for today. I will see you again on Wednesday. Have a great day.